Intel, probably one of the best known CPU manufacturers in the world, the people who gave us the PC, more or less. They created some of the most successful lines of processor we've ever seen, like the Pentium for example. But they've also created some absolutely spectacular lemons of a CPU. And for some reason, this channel has decided to document quite a few of those lemons. So far we've covered the Itanium. Boy, and how was that a major lemon. We've also covered the complete and utter lemon that was the iAPX 432, probably one of Intel's first major lemons. And now it's time to look at a chip that many people regarded as a lemon, but I'm not too sure, the Pentium Pro. But before we get into that, we're just going to have a brief word from our sponsor, PCBWay. The company whose major activity is sponsoring YouTube videos, who has a side hustle in the production of PCBs. Yes, upload your design, hand them some money, PCBs back in the post. It couldn't be simpler. Give them a bit more money, you can even have some components on your PCB when it comes back in the post. You can also send them your 3D CAD designs and they'll CNC or 3D print things out for you as well. They really do like upload file, get thing back in post. That really does seem to be their thing. Well, when they're not sponsoring YouTube content, that is. In order to get into this discussion of lemon or not lemon for the Pentium Pro, we're going to have to fill in a little bit of the backstory. Intel had not so recently released its most successful processor to date, the Pentium. Its long-awaited follow-up to the 486. The Pentium represented a huge leap forwards for x86 kind, as it had finally managed to go superscalar. By which I mean, it could actually run more than one instruction per clock cycle. And the CPU itself would take instructions from the pipeline and work out which ones to run at the same time. In fact, it even had 2 integer pipelines. It also gained a significantly faster floating point unit as well. But for the earlier versions of the Pentium, that floating point unit didn't necessarily do divide properly. But even with that major publicity millstone around its neck, the Pentium had sold like no other Intel processor before. Now, it was a much better processor than anything Intel had made prior to this point, but also timing-wise, it couldn't be better. Computer usage in the business and home and every sphere of life was exploding, and Microsoft had released a new version of Windows in the form of Windows 95 that honestly really did kind of need a Pentium to not run like a snail on Mogadons. So this meant that Pentium systems were flying off the shelves, and Intel, well, they were riding a pretty big high at the time. And it's with all this as the background that Intel decided to release the Pentium Pro, its next generation of processor. The architecture for the Pentium Pro would become known as i686, or at least in most Unix circles it would be. And it's the first time Intel swaps to doing the whole you feed it CISC instructions, x86, and it breaks them down into a series of micro instructions. Essentially, it's CISC dynamically being translated into a series of RISC instructions that the CPU actually runs. All x86 compatible processors these days does it this way, but this is the first chip to do it, and this meant that they could do things like speculative and out-of-order execution, and those features help avoid really expensive, in terms of performance, pipeline stalls. They also introduced a lot more stages into the pipeline that again sped things up considerably. They also substantially improved the support for SMP, symmetric multiprocessing, which meant instead of just having 2 processor systems, we could now have 4 processor systems. This is also the first Intel processor where we get to see physical address extension, PAE, which allowed for 36-bit memory addressing, which meant we could use 64GB of memory. Potentially. Of course, in 1995, no one has 64GB of memory, or enough money to purchase 64GB of memory. But heck, you can access more than 4GB, which is the thing that really mattered at this point, particularly if you had a 4-processor system. Now, while all these multiprocessor and extra memory features are not particularly useful to your average desktop user, it does now mean that Intel has a CPU that can compete with the big boys from Sun and SGI and HP and DEC, etc. You can now, in theory, assuming you're prepared to run Windows NT, run actual server workloads on this thing that would only be doable before on the bigger Unix boxes and Super Minis of the day. So you might be thinking, listening to all of this, so how could this thing possibly have been regarded as a lemon? Well, let's get to that bit. While the Pentium Pro was really good at running 32-bit code, stuff that used up 32-bit CPU registers and instructions, if you tried to make it run either 8-bit or 16-bit code, well, it did not run very quickly. And the reason for all of this comes down to registers. The next bit is going to get a little bit nerdy in regards to how CPUs work. So if this bit is not your bag, just look at the index below and skip forward a section, because we're going to get into the nitty-gritty of how registers do what they do in the x86 CPU line. Okay, right, have they gone? Right, I think it's just us nerds here now. Right, let's get into this thing. x86 processors only really have 4 general purpose registers that the software developer can make use of: A, B, C, and D. There are other registers for things like the stack pointer and the instruction pointer, etc., but they're not general. You can't just use them to shove your own values in without really messing stuff up. Now, 4 registers does not sound like a lot, and that's because it's not a lot. But for CISC processors, that wasn't a problem, because most instructions can handle being passed either a register as one of its arguments, or a memory location, or the memory location of a pointer to the memory location that's got the value in that you want. You see, CISC, complex instruction set processors, are not just complicated in terms of the number of instructions they've got, and some of them have a lot of instructions. I mean, you should have a look at VAX. But the actual instructions themselves are complex in terms of the addressing, i.e. you can pass registers, pointers to memory locations. RISC simplified not only the number of instructions that the CPU supported, but also the addressing, in that every instruction, apart from load and store, can only take a register as its arguments. So if you want to add 2 numbers, then you have to hand it 2 registers with the numbers in that you want to add together. You can't pass it 2 memory locations that store the numbers. Essentially, any data you want to do anything on, you have to load into a register with the load instruction, which is one of the only 2 instructions that happens to take a memory location. And when you want to write it back to RAM, then you use the store instruction, which again is one of the only 2 instructions that takes a memory location. So this means RISC CPUs have a lot more general purpose registers because, well, it needs them. So take ARM for example, it has 16 registers, of which 14 are available for general purposes. Spark has an even more complicated system with register windows. And Intel, well, it wants to take its big CISC instructions and break them down into micro RISC style instructions, and it's only got 4 registers. This is going to be a problem. And the Pentium Pro solved this in a way that all other Intel processors from here on out would also solve it in the same way. In that an Intel processor does not only have 4 registers anymore. It pretends it's got 4 registers. The instructions you can feed into it can only use 4 registers. But when the processor decodes those instructions in the pipeline, it remaps for each instruction's registers A, B, C, and D to one of a myriad of internal registers that it has. Ones that we don't know the names of and can't see from outside the processor. And it's this process of remapping the registers around that didn't work very well for the 8-bit and 16-bit code. Because as Intel made these processors more powerful in the line, they started with 8-bit, then 16-bit, then 32-bit, and finally, as we have today, 64-bit. Now, in order to keep the processors compatible with what had gone before, they still stuck with the same 4 registers, A, B, C, and D. And each time we went up from 8 to 16 to 32-bit, they made the register bigger. Well, sort of. In the Pentium 486, 386, and Pentium Pro, all the registers are 32-bit in size. But we have names that can access the 16-bit version of that register and the 8-bit version of it. So, the full title of Register A, for example, is EAX. And for Register B, it's EBX, Register C, ECX. So on and so forth. If we want to access the 16-bit version of that register, so Register A, it's AX, Register B, BX, C is CX, DX for the other one. Now, loading a value into the 16-bit version of that register affects the bottom 16 bits of the whole 32-bit register. We're also able to access the bottom 8 bits of that 16-bit slice as well, and the top 8 bits of it as well. So to get at the top 8 bits of register A, we go for AH. To get the bottom lower bits, we go at AL. Same BH for the top 8 bits of the 16-bit bottom block of B, and BL for the lower 8 bits of the 16-bit block. So using this system as a slightly different version of the label tells the processor how many bits to load into a register, or how many bits to use from a register, could create issues when you're re-aliasing around every single register when you're making this CISC to RISC instruction set mapping. And this is what lies at the heart of why the Pentium Pro is so bad at running 8/16-bit code, as each time you came to one of these partial accesses of the 32-bit register, well, it ended up flushing the pipeline. And that is hugely expensive. You flush the pipeline, there's all the clever pipelining features like out-of-order execution and speculative execution and all the superscalar stuff just goes right out the window. You do that pretty regularly and what you're left with is essentially a 486. And if you'd spent all the money you'd spent on a Pentium Pro, you did not want the performance of a 486. But it turns out, a lot of compilers, also when they produce 32-bit code, made use of the 8 and 16-bit versions of the register, because prior to Pentium Pro there'd been no penalty for doing that. So let's go over what would be a fairly common output for a compiler when dealing with strings. So what we're looking at here is the assembly equivalent of strlen, a function that's there to get the length of a string, and it works by taking a block of memory and iterating over it until it encounters the 0 byte, as in the null character, which is used by C in other languages to indicate that the string has ended. You may have heard the phrase null terminated string, well that's what this is. So in principle, our code would take the block of memory we're looking at, step over it 1 byte at a time, checking to see if it hits the 0 byte, or null as we call it when dealing with strings. Now on a 32-bit system, you do not want to read RAM 1 byte at a time, because the processor can grab 4 bytes in one go. And in fact, on some 32-bit systems, it can't even do non-aligned reads. You have to read a 32-bit block from the 32-bit boundary. You can't read partway into that 32-bit block. Now, x86 does let you do non-aligned reads, but boy and how does modern RAM punish you for doing that. It can be substantially slower to read one unaligned byte than it is just to grab the whole 32-bit block from the aligned boundary. Now, luckily with a lot of x86 chips, the CPU cache would save you from that unaligned read and just do an aligned read anyway, and just take the byte out of it to put in the pipeline. But that's not a behavior your compiler should be relying upon. So most compilers of the time would produce an output that kind of looks like this. Now you're going to notice me using two registers here that I've not mentioned before, and that's ESI and EDI. Now they can be used as 32-bit general purpose registers. They also have other functions, and the only reason I'm mentioning them here for the first time is I didn't want to complicate up the previous section when talking about the 8-bit and 16-bit access to registers. So here we have the source written out in Intel style assembler, so it's kind of got the arguments backwards from the way you might expect. So the first thing you see it doing is setting up a few registers. That's so when this inline block of assembler has finished, we can tidy everything back up the way it was before the function was called. Well, I say function, it's really just a block of assembler. The next thing we do is get into the block of code where we're going to loop over our data. Now, you'll see this bit where we're moving data into the 16-bit version of register A. And the assembler is saying it wants to grab a word, which is 16 bits, from the memory location pointed to by the value in the ESI register. That's what these square brackets mean. It means from the memory location that's stored in register ESI, not the value that's stored in register ESI. We then grab another 16-bit block from the address pointed at ESI, but 2 bytes further along in RAM, which is an unaligned read on a 32-bit boundary, but an aligned read on a 16-bit boundary. Again, Pentium Pro isn't going to like that unaligned 16-bit read. We then compare the lower 8 bits of the 16-bit block currently stored in A, i.e. 1 byte, see if it's 0. Is that a string terminator? Nope. Then we check the upper 8 bits of the 16-bit block stored in register A. Is that 0? Nope. Move on. We then do the lower half of B, the upper half of B. If none of those are 0, then we increment ESI by 4 bytes, or 32 bits. Then we loop back round and we read 2 16-bit blocks and compare them again. And so on and so forth until we find the 0 byte that terminates our string. Or we segfault because no one terminated the string. But using this approach, by just doing 2 memory reads we can compare 4 bytes, as opposed to doing 4 single byte memory reads. And we also have the advantage that at least one of those reads is aligned on the beginning of a 32-bit block, and the other one's at least on a 16-bit block. So it's only every other read that's unaligned to the beginning of a 32-bit block. And this is why compilers still make use of the 16-bit versions of the register and the 8-bit versions when compiling 32-bit code, because that's always been faster to execute, as it results in less memory reads. The problem is, for the Pentium Pro, this triggers multiple flushes of the pipeline, and so performs like absolute garbage. Right, hopefully for those of you who skipped ahead, we're all now back together, and my viewer retention graph for this video is going to look really weird. Sorry, algorithm. So for those who skipped the last section, 16 or 8-bit code caused the CPU's pipeline to flush, which really knackered the performance of this thing. But why would this be a problem in something called the Pentium Pro that's only intended to run Windows NT and server software on top of that? Well, part of it was in the choice of name, Pentium Pro, because a lot of people, including a non-trivial percentage of gamers, saw the Pentium Pro as, well, that's the better version of the Pentium, right? And yeah, if you run the right code, it is better than the Pentium, assuming you're running 32-bit code. If not, then it performs considerably worse than the Pentium, or at least at the same clock speeds. So if you're going to run Windows 95, that despite the fact that Microsoft kept referring to it as the 32-bit operating system, a huge chunk of its code base is 16-bit, it's absolutely riddled with 16-bit code. And even when some code is 32-bit, it, for performance reasons, has been compiled to use 16-bit versions of the registers that still cause the pipeline flushing issue for the Pentium Pro. So even some 32-bit code still runs like a dog, i.e. the bits that try and do 16-bit and 8-bit tricks. Then there's the business users who bought this thing because it's the Pro version and stuck Windows 95 on top of it as well. They also discovered its performance kind of sucks, which is the exact opposite of what they were expecting, again, because that entire codebase is riddled with 16-bit code. And even when they went to run Windows NT Workstation on it, or Server, which is a 32-bit operating system, where all the code is genuinely 32-bit, a lot of the applications they then went to run on top of that operating system were again riddled with 16-bit code. Because the world of Windows had really not truly transitioned to 32-bit by this point, because with the Pentium and Windows 95 there really wasn't much point. The only users who were really having a good time with this thing was the people who run Unix on this thing or Linux, because all the code for them had been compiled as i686. Pure 32-bit code didn't try to make any clever 16-bit or 8-bit uses of the registers. And in 1995, there are some Linux users. There are not a lot of Linux users. I mean, it's me, Mike, and Bob, I think, and some guy called Linus. And this is where the reputation of being a bit of a lemon came in for the Pentium Pro, because for a whole bunch of its user base, yeah, it was a bit of a lemon. For the lucky few who were running 32-bit operating systems that were purely 32-bit operating systems with 32-bit applications, then it was the best performing chip that Intel had ever made. And this is the thing, Intel did not have in mind when creating this thing running old 16-bit and 8-bit code. Their assumption is this would be largely for people running NT, a full 32-bit operating system that would have applications written for NT, which again would all be 32-bit. And for some Windows NT users, this was true. The company I worked for at the time ran NT Server, and we ran a 32-bit version of Sybase for NT on top of that, which was built for the Pentium Pro. And it needed to, because it used a terrifying amount of RAM for the 1990s. And that version ran really, really well. It didn't perform quite as well as it did on our Sunboxes, but our Pentium Pro machine cost like half as much as the Sunbox we were running on it, so let's not die of shock. So if you read a lot of articles looking back at the Pentium Pro, you'll see it characterized as, what a lemon. Couldn't run 16-bit code to save its life, and almost all code was 16-bit. Far too ahead of its time. And that's the nice version of the write-ups you'll see about it. But the reality is that there were people running 32-bit workloads at the high end, and that's who Intel created this processor for. And with the premium they charged for it, yeah, it was probably worth it for Intel. So I'm going to say that this processor is not a steaming pile of lemons that some people seem to think it is. So what happened with the Pentium Pro? Well, Intel did sell them in the kind of numbers they thought they were going to, at least to the market segment they had in mind. They also sold them in numbers that they didn't expect to market segments that, well, they didn't have in mind. And it'd be fair to say that those users were not overly happy with their purchase. And that was the curse of using the Pentium name. Sticking the name Pentium in there made people think that this was just an upgraded version of the Pentium that they already loved. It turns out that even when you explain stuff like it's only really good at running 32-bit code, some people just don't pay attention to that sort of thing and just go, but it costs more, it must be better, and then find out that it is not for their use case. Now, Intel also managed to make some really high-profile sales with this thing. The Pentium Pro was selected to create what at the time was going to be one of the world's largest supercomputers, the ASCI Red, the first ever supercomputer to do over 1 teraflop. First operational in 1997 and finally decommissioned in 2006. At its peak, it had a grim total of 9,298 Pentium Pro processors, with 1,212 gigabytes of RAM. This monster machine managed to drink down around 850 kilowatts of electricity when operating. It's a good job it was owned by the Department of Energy, because who else has got that kind of money for an electricity bill? As for what they ran on it, well, we know it's got stuff to do with nuclear weapons thanks to a test ban treaty, but apart from that, if anyone tells us anything more about it, they're probably going to end up in prison. But for Intel, this thing was a major headline grabber. They finally got their foot in the door of a computing space that they'd never been in before. And although they were far from the biggest player in this space, I mean that probably went to the likes of Sun and SGI and IBM, but it meant Intel's processors were now up there with the big boys, as it were. Which, despite the sheer volume of sales that Intel had made of its x86 processors, it had never been in this space before. So, despite people regarding the processor as a bit of a lemon, in some circles it had also gained Intel a lot of prestige by getting into the supercomputing space, and kind of into the high-end workstation and server space as well, at least as far as NT workloads goes. So, what's the legacy of the Pentium Pro? Well, the Pentium Pro was underpinned by what Intel referred to as the P6 architecture. And that P6 architecture went on to be what underpins the Pentium 2 and the Pentium 3. Now, it gained some extensions in that the MMX instruction set that was first pioneered on the Pentium, well, that got added to the Pentium 2. The Pentium 3 then saw an improved version of that known as SSE, which allowed the P6 architecture to do all the single instruction multiple data things that allowed all sorts of performance improvements. And by the time we get to the Pentium 2 and the Pentium 3, well, Microsoft has released Windows XP, which is essentially the NT codebase, which is all 32-bit. So that means relatively few people are running the 16-bit/32-bit version of Windows that's still sort of built on top of DOS. You know, the whole bag of soup that was Windows 95, 98 and, unfortunately, ME. The gaming market is also radically transformed as well. No longer are most PC games targeting MS-DOS. They're now all targeting a 32-bit version of Windows using DirectX and Direct3D. Meaning that we just don't have the 16-bit and 8-bit code that we used to, so it doesn't really matter too much that the P6 architecture doesn't handle that stuff particularly well. Although I believe there were some improvements to the P6 architecture that made it deal with it better than the original Pentium Pro did. Largely by adding segment register caches, and also for accessing 16-bit or 8-bit chunks of the 32-bit registers, they added an internal flag to skip pipeline flushes, well, wherever possible. So this combined with the higher clock speed of the Pentium 2 meant that it ran 16-bit and 8-bit chunks of code at a very respectable speed and significantly quicker than the Pentium did, for example. So people buying the Pentium 2 saw an improvement in speed of execution of all their code, be it 16 or 32-bit. It's just the 32-bit code is still a bit more performant than the 16 or 8-bit code, or register accesses. Chips based on the P6 architecture would stay into production until 2007, when the last mobile version of the Pentium 3 rolled off the production line, which meant that all in all the P6 architecture had a production lifespan of 12 years, which for a CPU microarchitecture is quite an impressive run. It's also the first time we had an architecture that coped well in the desktop plugged into the wall space and the mobile laptop space too. Prior to this, the mobile version of say a 486 or a 386 or even a Pentium was kind of rubbish compared to the normal version. So this is a period where we really see the whole laptop space start to explode, and they're not having to be such the trade-off between is it portable or does it perform well. I mean, the mobile version doesn't perform quite as well as the desktop variant, but the gap is nowhere near as noticeable. Well, if you got all the way to the end, I'd like to say thank you very much for watching. And if your recollection of the Pentium Pro was, what a steaming pile of lemon, then I'm hoping this video has gone some way to you re-evaluating that lemon-based belief. And I'm also looking forward to discussing this with some of you in the comments section, which is conveniently located beneath this video. I'd like to say a huge thank you to Matt from Tech Made Easy, whose ARMS and Pentium Pro unboxing has featured fairly heavily in this video. I really wanted to be able to show an actual physical Pentium Pro in this video, but I didn't want to just buy one as a prop. I mean, these things are getting hard enough to buy without YouTubers buying them up to use them as props in videos, so Matt was kind enough to let me use his footage. So cheers, Matt. You will also in the description below find a link to Matt's original unboxing video and, all his stuff in general. Go check it out. He's a really nice guy and the videos are, I think the sort of thing that will interest all of you. Also, beneath the video, you'll find a very convenient button to indicate that you enjoyed this video if that was the case, and there's another button if not, and, thanks for the engagement. And if you'd really like to help the channel out, there's another button labelled subscribe that apparently helps the algorithm tell people that these videos actually exist.